Cool. I think we are live.
All right, I'm just gonna
Yes, we are. Maybe give it like 1 minute and then we can dive in.
Oh yeah, well, good for a little buffer.
I can see 3 people, 5 people are here. Awesome. Maybe 1 minute instead of 2. All right, I reckon we are good to go. 1 minute in, 10, 12 people watching. So for a quick intro, I'm Samara from the Cantina team, and we've got Zach here today to talk about turning the OP stack into a ZK chain using SP1, which is very exciting. So I will hand it over to him.
You're going with ZK. Even the Brits usually give in and do.
I'm Australian. I'm Australian.
All right.
We do things differently.
Fair enough. Very cool. Okay, this is great, guys. I'm excited to walk through this. I've been working on it for the last few months, so it's fun to talk about publicly and share a little bit. I know, yeah, this isn't like very security focused. It was more of a project to build something, but I know there's a lot of interest in OP stack stuff and interest in ZK stuff and ZK stuff. So gonna try and do like a whirlwind tour of those things and how they come together and how this all works. I will say there's like a decent amount of context that's needed for the different pieces. So my plan is to kind of like move quickly through the building blocks that build up to it, and then try to pause after each of them to do like questions. Samara, I don't know exactly how that works here, but if we could make that happen, I think it's important for people to like absorb a block fully before we build on it, or else nothing at the end will make sense.
Yeah, I think if people have specific questions, if they want to just drop it as a reply to the Twitter post, I can stay across that.
Perfect. Okay, I'm gonna share my screen, and then we are gonna start with just like a big picture overview of how optimism works. So I got optimism in 5 minutes. If we're doing a talk on all this stuff, we got to move quick for this. Cool. This may be a recap for some of you, but it'll give some context. So basically, optimism is made up of like contracts on L1, and this is true for most rollups, but we'll talk about OP stack specifically, and then software that is running the L2. So in the most basic form, like from a user's perspective, let's say we just had the sequencer. So this is like OP-geth running in sequencer mode, and what that does is it takes in transactions from users, it assembles them into blocks every 2 seconds, and then we have and basically like runs the chain as if it is just on its own and there are no other nodes or anything else. On L1, where the user interacts is through the bridge, but in the end, it basically goes to this optimism portal contract that handles deposits. So basically like putting money onto the chain. And this portal then talks to OP-geth and says, hey, include those transactions as well. So this is like the building block, like the basic piece of what a user is doing. But if this is all there is, then this is like basically a Web2 company, right? It's like they have a server, you're sending things to it, it's doing work. To start to move towards it being a blockchain, first thing you need is like the ability for other people to run nodes. And so how do these nodes know what's going on? Like they're not just going to this one and saying like, tell me what to do, because that's like not very secure. So what happens is as OP-geth is running in sequencer mode, there's this other piece of software, OP-batcher, that is taking each block, it's compressing it, basically like all the transactions that will happen in that block into some format. They've changed it over the years, but like the most compressed they can make it. It's going to pass those transactions in the past in the form of call data, but now in the form of blobs to this batch inbox. And the batch inbox isn't a contract. It's literally just an EOA address where the transactions are sent that hold all this compressed data that represents each block on L2. And then for a node to run, what's happening is this OP node piece of software is watching the batch inbox, it's watching the portal for deposits, and it's running some computation to say, from all the data of what's happening on those, we can turn that into a set of transactions. And then we have a local version of opget running that's not in sequencer mode, and it executes what op node gives it. So with everything here, we basically then have a centralized server that is taking in transactions, forming blocks, then is posting all the data, and then the ability for any individual to run nodes that then take in that data and calculate where the chain is at that point. So that's like useful, but not that useful because there's no way to prove where the chain is. So like this might work well if like basically like if we had like a company where we wanted to synchronize information and I was running all the information and everyone wanted a like provable way to make sure that they were tracking with it, that should be great. But if there's a disagreement, or if I say my opget showed up something different, or the sequencer is lying about something, there's nothing you can really do with this. And the biggest implication of that is like can't do withdrawals, right? Like how do you on L1 show anything about the state of L2 that doesn't exist? So this is where the last piece of the system comes in. There is what used to be the L2 output oracle. That's just a contract that takes in a hash representing the state of the chain. Now they use these fault dispute games. And there's a piece of software called OP Proposer that is similarly to how the batcher's talking to the sequencer and grabbing the data to post the blobs. This is talking to the sequencer, grabbing the state, and at some regular interval, posting the output route to that contract. And the output route, it doesn't really matter. It's basically just like, you could derive all the same information if you just had the block hash. It's just a way of taking the block hash and some other information about the block so it's more easily accessible. So now that we have that contract that has the output route, has some definitive information about the state of the chain, now the portal can validate withdrawals based on that state, right? You can imagine opget runs a block. That block shows that a person withdrew funds. The state is now captured. It's posted on L1. Now, when I want to withdraw funds, I can look at that contract and say, hey, can I prove that I did that withdrawal based on the route that has been verified? And in the current way, the current system, the way that works is that output route is posted. Any proposer just basically posts it, doesn't post any proof or anything. And then there's a challenge window where people can go back and forth disputing it and settle that challenge in order to make sure within 7 days that all those output routes are valid and can have withdrawals against them. So this is like optimism as it currently stands. Now, if you look at this, it's like, at first I was like, okay, we want to make this into a ZK chain. Like there's so many moving pieces. How do they all fit together? But the reality is like this sequencer is just taking in transactions and executing them. This batcher is compressing them and posting them. This node is just reading them and doing it. All these pieces don't really have to change, or don't have to change at all. The things that do have to change are, first, this L2 output oracle, instead of having a fault dispute game, instead of trusting the proposer, it literally can be changed to just be the exact same, but require that you post a ZK proof of that execution in order for the new output route to be added. Second change, this OP proposer that used to have the fun, easy job of just taking the state and posting it every hour, now has a bit more complex logic because it needs to calculate the ranges to calculate proofs over and manage the proof generation and keep track of all the proofs that are in process and all these pieces. So it gets a little more complicated. And then the biggest piece is that there needs to be a way to actually make those proofs, right? This thing can ask for proofs for certain block ranges, but we need to be able to actually create a ZK proof of a transition between states. And that's where the meat of the project is. So for today, I'm not really going to talk about this contract. It's relatively simple. You can look at the diff, but like it just does what it otherwise did, but verifies the proof. I'm not going to talk about the proposer. It's a big change, but most of it's just like plumbing. It's not that interesting. What I am going to talk about is this proof server. Basically, how does this proposer call out to an API and say, hey, I want a proof from block A to block B, and that this proof server is actually able to return a ZK proof that shows that state transition is valid in a way that's trustable. So I'm going to pause there for a second before I get into it. Any questions about this whole thing? I know that's a fast tour of a full chain, but Samara, maybe if you could check if there's any questions or things to clarify before we move on to like, how is that proof generation possible?
Yep, I'll jump into the replies now. I can't see any questions, but yeah, that was the fastest overview ever. I love it.
All right, doing my best. Hopefully everyone's not confused. Good. So
if anyone has questions, as I said before, just pop them in the replies of the post, and I'll get Zach onto them.
And I've definitely found like a lot lot of this stuff, because there's so many pieces, it's like, it's easy to just kind of like know the word and not really understand it. So like, even if you think it's a dumb question, I am sure other people have the same one. So please ask, and tomorrow just interrupt me if things pop in there that are relevant. Cool. Okay, so let's take that now. We're going to do a little detour and talk about SP1, because it's kind of hard to reason about like, okay, we're going to send something off to a server. It's going to generate a ZK proof. Like, what does that even mean? What is it proving? It's returning a bunch of numbers. How do I know those do anything? And what's interesting, I guess, is like, as a starting point, we can put ZK aside completely, and we can basically simplify this into like, can you write a program that if someone could see the full program, and they knew the output of the program, or they knew some values that were a part of it, maybe some of the inputs and the output, that you could prove something, and forget that ZK exists at all. So what I'm actually going to do here is, let me go into the demo one. So as a starting point, let's look at this. Imagine we have this program, right? And so we've got a target hash, and all we're going to do within the program is we're going to take the first input from the user, we're going to hash it, we're going to turn it into a string, and we're going to assert that it's the same. And so if you had this program and someone was able to show you, yes, I ran this program and it didn't error on this assertion, then you know that they have the preimage for that hash, right? I can say cargo run, blah, blah, and it's going to fail. But if I say cargo run Cantina, which is the preimage of that hash, it verifies. And that's clearly, there's no ZK involved here. But all we know is we know what is in this program. We know the logic that is here. We can read that. And that gives us enough information to know that we can verify something about what the user inputted. So what's cool with SP1, and what is truly just feels magical, is that like, this is not that different from the way you have to think to build something in SP1. Basically, you want to write a program, which is, we'll get into this program here, which is run in the ZKVM. It is pure Rust code. I've had the experience of like, when I was first learning Noir, it's like, wow, this feels just like Rust. It's so easy to learn. But this feels like a different level, because it's like, it is Rust code. So you can just like import packages and literally treat it as if it's just Rust. And if you know that it runs and behaves and works the way you expect, then it will generate a ZK proof based on this. So it's doing exactly what we just did here. It's saying, I know the program, I know whatever inputs, I know outputs, I know it ran, and it's creating a ZK proof that summarizes that, and you don't have to touch any ZK at all in order for that to happen, which is kind of crazy. So let's look at how that works. In any SP1 program, there are two crates. The first is the program itself. So this is what's run inside the ZKVM that is being proven. And then there's the script, which is like what sets everything up and runs that other program. So what you can see is like this program here, when we compile it, it compiles in a specific way so that it is saved as this elf here. And then when we're calling the prover, we are passing the program's the program's bytecode as well as the inputs, and it's doing everything that we need there. So let's go through this example that's a little more interesting than the hash, and look at like what this would look like in practice, right? So if you look at this program, reading is just reading the inputs, committing is making something public so that it can be verified. So all this program is doing is it's taking input X, it's taking input Y, it's multiplying them, and it's committing to the result. So what you could think of this as an example is like, if I'm trying to prove that a specific number is not a prime number, I might write a circuit like this and say, okay, these two are both private. If someone can input an X and Y that create that result, then they've proven that it's not a prime number. And this example here is like, okay, we have a target of 10. Someone inputted 5 and 2. We can write both those into the program. We can run execute. Execute is like a shortcut in SP1 where it basically runs the same process as it would, but doesn't actually generate the proof. So it's a lot faster, but you can just change that to prove and it would actually output the proof. And then we can pull out whatever public value was committed to and assert that it actually equaled the target. Now there's a few problems here. I was thinking that there'd be more ability to interact, but I'm not gonna make people post answers as Twitter replies. But you might realize there's actually a problem in this code. And this is what's interesting is when you look at ZK stuff, often a lot of the security implications, it's talked about things being under constrained. And it's easy in ZK land to like make that sound more complicated than it is, or to feel intimidated by it, because it's like, what do these constraints even mean in a lot of these cases, especially when you're at the lowest level. But in the case that you're writing just like plain Rust code, the same thing is true, right? You have to be sure that if this program succeeds, it's actually proving what you think it's proving. And so in this case, as an example, if we were trying to prove that 7 was not prime, well, that shouldn't be possible. But if we make this a 1 and we make this a 7 and we go into script, we can say and it's going to prove that 7 was not prime. So we got an issue there, right? So we've got to update this program and add in all the constraints that really matter, right? So in this case, it would be like assert that x doesn't equal 1 and assert that y doesn't equal 1. And there we go. Now it's going to catch those assertions, it's going to fail, and it's not going to let that pass. But again, we might have another problem, because in this case, as in many under constrained bugs, when it's in release mode, Rust will let you overflow. So I actually grabbed the actual numbers here. But if I replace these 1 and 7 with these two numbers, again, it's going to let me prove that 7 is not prime, because these two, if you multiply them, are going to wrap around in a way that lands us back on 7. So as you can see, like, it's tempting to think like, oh, ZK is abstracted away, I get to just write code, but it still requires that same kind of thinking. And I think it's why it's important from a security perspective to say, like, all you've done is concentrate your assumptions into this code, and you still have to do the same thinking about constraints and making sure that it is rock solid, that this actually proves what you think it's going to prove. So with that in mind, we now basically understand how SP1 works, which is you write one program, it is proving a thing, and then you have another script that sets things up, passes data into it, executes it, and then takes the proof. I'll pause for a minute and see if there are any questions at this point before now finally we can get into the details of how to then take this very simple structure and start plugging the things in that would prove the execution of an OP mainnet block.
No questions that I can see in the replies yet, so feel free to forge ahead.
I must be explaining it so clearly. Okay, great. So now we've got like the setup for the challenge. We know that if we go back here, what we're trying to do is allow the proposer to call out and say, I want a proof that from block A, we were at this point, and that at block B, we're at this point. And we know the way that we're going to do that loosely is that we're going to have some program that takes in some inputs, and if it succeeds and outputs the output root of the end, then we know that that output root is valid. So let's get into this code, which is what actually does that. And I guess before that, huge shout out and like backbone of this is Kona. So Kona is something that the Optimism team built. It's not in production yet, but will be at some point. And Kona is basically their implementation of doing this transition, the state transition between blocks in like the most simple no STD Rust code that could be used. And they use it for fault proof. So they use this so that they can like compile things in a very simple way in order to run it on these fault proof engines. But the backbone of that is very similar to what we need. So that allowed us to basically start from that place where we didn't have to re-implement the entire derivation process or execution process, and instead just using their building blocks, adapt it in a way that makes sense for ZK. So I guess the easiest way to start is like, now you'll recognize this, like we had the programs client in the SP1 example. These are our programs. So these are the things that will go straight into the ZK VM to be proven. And what's interesting here that you'll see is like, you can see a lot of the logic. And Samara, I guess, give me a quick, like, can you read this code or should I be making it bigger? Maybe that's better.
Yeah, that's perfect.
Cool. Okay. So you can see a lot of the code is like, it's got these config ifs where we are basically checking if we're in ZKVM mode or not. What that's going to do is when we're compiling it for the ZKVM, it will do one set of things. When we're compiling it normally, it's going to do another set of things. And the reason that that's important is the way that this is possible is if you think about, like, there's no way to execute all this in a ZKVM because, like, we don't have access to any of the data. And we can't just say, like, hey, from the ZKVM, let's just, like, call out to the API of a random node and ask for the information and then trust that. So what we need in the ZKVM context is a way to do this in a way that is completely self-contained, right? That we, like, have every input we need in a trusted way that would allow us to rederive the entire thing. And the way that that's possible is we first run it in what we call witness mode. And it's the exact same logic, but what you can see here is we use this caching oracle. And what we're going to do, let's say we're trying to prove a specific block. It's block 10,000. And we know the pre-state. We know what we're trying to get. What we do is we load in some basic set of starting points. So those include a trusted L1 head, which we have because we're doing this verification on L1. The last trusted L2 route, which we have because the contract has previously proven things. So we know a baseline of where we're starting from, as well as, like, the config of the chain and some other things that we can be certain of. And then when we're running this, we're going through this derivation process, which is looking at the L1 blobs in order to reconstruct what the transactions are. So if we go back to this keynote, that's doing what this OP node of a node is doing, which is looking at the batch inbox in the portal and pulling out all the transactions that we would need to execute in order to execute the block. And then once we have that, it's putting it through this stateless executor. So it's saying, we have the starting point, we have all the transactions, now run all those and see where we end up. The magic of this witness generation run is rather than just doing all that computation, it's doing each step, and every time it accesses any state, it is saving whatever hashes are necessary in order to prove that state. So, like, the simplest example of this is I'm going to send some ETH to someone. It needs to access my state to know I have enough ETH and to see my new balance. And so it is going to, up from the state root, calculate all the hashes in the Merkle Patricia trie to get to my account, which therefore will be able to prove the balance of my account. And it's saving all those pre-images so that later, if we didn't have access to anything, we know the state root, we can redo all those hashes, or I guess undo all those hashes to work our way back down to uncover my account without any access to external data. So basically what we're doing in this run is we are running this whole derivation process and execution process, looking at L1 and L2, and we are saving every pre-image of every hash that is accessed, as well as some other things around precompiles and KZG commitments and other things. But we're saving all of that while we run it. So that's, like, the first pass of what has to happen. Now we've got the same program, but we also now have a data folder that's holding 50 or 100 or 200,000 pre-image and hash pairs. And when we rerun this in the ZKVM mode, we're passing all those things into the ZKVM, and we're calling this oracle.verify function. And if I look at that, what that's doing basically is saying, okay, we've got all these pre-images of hashes. For each thing, go through and verify if we have a pre-image and a hash, that those actually fit with each other, right? So it's going through and verifying every piece of data in the entire database before we start, so that we know that if it's something says this is the pre-image of this, it's true. And then it's going to go and do that exact same derivation process and the exact same execution process that'll prove the exact same thing, but without any access to external data. Instead of accessing anything external, it's just going to use all that data that it has stored in order to do that. And so what that allows us to do then is that what we are sending to the ZKVM is a bundle of data that is 100% verified within the ZKVM, and then is used to execute the full derivation and state execution to get us to a new point. And at the end of that, we're, based on the state of that executor that's run all those blocks, we're computing the new output route, and we're asserting that it equals the route that was claimed on chain. And if that's true, then the magic ZK proof that pops out of SP1 based on running this code, and again, you can pretend ZK doesn't exist, and that we can just see all this code and know that if it runs, then we've proven that that fact is true. The ZK proof is just doing the same thing. Then that can be used on chain to verify that block. The question then becomes, like, I guess a few things. First, in this derivation and execution, how are we actually able to do that? Like, how much data has to be fed in that's trusted for us to derive all the payloads in a block? Like, that seems like it would be difficult. And the really interesting thing here is, like, the minute where we propose the proof, we know the block hash of L1, right? We can just like access that with the block hash opcode. And within that block hash, if we open it up and look at the pre-image of it, we can see the entire block header. And one of those things is the parent hash. And if we grab that parent hash, we can open it up, and inside that we have the whole block header, and we can see the parent. And we can keep doing that all the way back to the L1 blocks where the blobs were posted, that included all the transactions for these L2 blocks, right? Like, if we go back here, these are posted to the batch inbox. These are a bunch of transactions, just like normal transactions to this EOA. And we can, from our current block hash, walk back as far as we need to reconstruct all of the transactions that are going to be a part of needing to execute this block. So all we need is the L1 hash, and that's sufficient for us to be able to then work our way back and pull out, to basically do everything that OP node is doing, as long as we have all those pre-images, right? We couldn't just start with the current block hash and magically figure it out. But if we've done this witness run and we know we've saved the witnesses for the pre-images of all those block headers, we've saved the witnesses for every transaction that is going to need to be accessed in the transaction tree of that block, and all those pieces, then we're able to magically, just from the L1 hash, work our way back and get that data. And then similarly on the execution side, what do we need? Basically, all we need is that last trusted L2 output route, which we have from the contract, as well as the config of the chain, which right now we are pulling from like the superchain registry. That makes it easy, but by the end of the day, we're pushing an update where basically you can like store that hash on chain to verify that the config that was passed is valid. And so with those two things, we can run this execute payload and know that any execution that's going to happen is fully verified. So it's kind of this magic thing where, like, at first I was intimidated by how much trusted data we might need, but realizing that like all of this pre-image stuff can get verified in the zkVM by just calling this verify function, and that the only real trusted things we need to make this happen are any L1 block hash that happened after all those transactions were posted to blobs, as well as the last L2 claim block and some config data for the chain. And if we put those together with the right pre-images, we can recreate all that execution. And again, if we can prove it, if we can have a Rust program that definitively proves that state transition, then we can, with SP1, have a ZK proof that does the same thing. The last thing on this that I think is worth touching on is, like, okay, all that works, but there are limits to what SP1 can do, right? So I can't feed in 10,000 blocks and say make a proof. First of all, that the pre-images for that would be like gigabytes of data, and the amount of computation would just be too much for it to be able to hold in memory. So what we do is we create these range proofs and we cap them at a certain size. We've played with the numbers, but it's probably somewhere in the 30 to 50 block range. And we just save those and hold on to them. And then, because I guess you could post those on chain every 30 or 50 blocks, but 30 or 50 blocks is a minute. And so you're going to be paying for a lot of gas cost for doing that ZK validation checks if you're doing that every minute. More often, chains are doing this every hour or so. And so what we'll do is we'll save all of those. This is all the logic in the proposer that's kind of managing this process. We're saving those, and we have another client program called aggregation. And this is like magically done by SP1 as well, where once we have enough of those proofs, we're able to basically pass a block of proofs in. And you can see this is just a program like any other program, but it's working on the proof level instead of on other inputs. And it's going to say for every 2 blocks, prove that for every 2 proofs, prove that the output root of the last one matches the input root of the next one, and prove that they're talking about the same chain ID, and we'll eventually add the same config as well. And so if that's true, now we've got a sequential list of proofs. We know that that's the case. And then within this proof, we can verify that those other proofs are valid, and then attest that this aggregate proof got us from the first one's L2 output root to the last one's block, to the last one's claim, and that this basically proves the aggregate of all of those blocks. And so loosely, our process for this is every minute or two, we're creating a smaller proof that's proving a minute or two worth of blocks. At some period, we have enough of them. We aggregate them all together, run this program that verifies that all of them are valid, and that creates a final proof that can be posted on chain and encapsulate the entire state transition from A to B. The last little piece here to touch on, I guess, like we can look at this, like the host files. So they're doing the same kind of thing we talked about in the other example, right? They're just doing all the setup. So they're pulling all the arguments for the native run. They're doing that actual native run that's generating the witnesses. They're creating the input to the zkVM, and then they're just calling the same prover.prove and saving the proof. Yeah, I highly recommend playing with SP1. It's like kind of magic how easy a lot of this stuff is, and that we just kind of get to forget about the ZK side and just focus on logic that is really rock solid. And I guess the last thing here is like, okay, so we have the proposer, and it wants to be able to just like call out to a server in order to generate these proofs and manage all of this. And so this kind of replaces for us a lot of the zkVM, a lot of the host stuff, like the script in the previous example, and just exposes a few like simple functions that recreate the logic of that host, right? They're getting the inputs to the native run. They're running that native host to generate all the witnesses. And then they're calling out to Succinct's prover network to actually generate the proof. So this is a cool feature of SP1, is that they've got this prover network that's still in, I think, alpha, but will be more public soon, where instead of us needing to like run all of this on a machine that can generate proofs, which they use like GPUs for and stuff, we just go straight to their prover network, just call into the API, pass the information for the input, and then their prover network manages generating that proof, and we can at any point just call like get proof status on it, grab the info we need, and pass it back to the proposer. So that's loosely the flow. It's like proposer is watching the chain every couple minutes. It has calculated that it's an optimal point to request a proof. It goes out to this server and says, hey, I want a proof that's going to prove a range of blocks. It's going to run this native mode to get the witness. It's going to call out to the prover network, Succinct's prover network, to generate it. And it's going to go on with its day. It's going to do this again. It's going to do it again. And as it's doing it, it's going to be checking the proof status. And when it gets fulfilled statuses back, it's going to pull that proof and save it in the database. And after some period of time, say an hour, it's going to take all those ones that are saved in the database, and it's going to call request ag proof and do the same thing. Go out to Succinct's prover network, pass all the data that it needs. And when that proof comes back, the prover network knows, okay, that means it's time to post on chain. And so it goes on chain and posts it, and we've transitioned the state of the chain. So that's, I mean, what's cool about this is like, it doesn't actually require breaking any of the like logic of the chain itself. So for us to be able to test this, we were actually able to just set up an OP Sepolian node, deploy this contract, which obviously like our L2 output oracle doesn't matter. No one's using it for withdrawals. But if they were, we deployed the contract, and we had the proposer running, watching the chain, making these proofs, submitting them on chain, and we're able to kind of have the chain live progressing as if they were able to use this. And there's some kinks, especially on like the amount of proof work that is needed, and making sure we're able to scale up to handle those like intense loads at times. But it's not far away, and Succinct's going to keep working on this to get it from like, this is a proof of concept that is working, to this is something that is like production ready for, not for OP mainnet, but for chains that might prefer to do things this way, have a priority on fast finalization times or less like stringent security concerns. So that's the overview, I guess.
Just jumping in with a question there. You just mentioned like having to scale up. What, from like a high level, what needs to be tested or changed to make that achievable?
I would say, okay, so I'd say there's a few things. One is like, we have run this on the live chain. If I was going to deploy this, I would be wanting to do a lot more of that testing. So like running it basically like from Genesis on multiple chains to make sure there's no weird quirks. The second thing is that there are certain precompiles that are really expensive, and Succinct is working on finding ways to like optimize the execution of those. But if there was a block that was like full of certain precompile calls, it would be a lot slower than it is currently, and maybe even too much to handle. And then the third thing is their cluster. So like the long-term vision for Succinct is that they will have a prover network that's like decentralized, and anyone can be generating proofs. for this beta at the moment, it's like proof of network of one. So like they're running the cluster that's doing it, just so that they've got the infrastructure to be able to start building around it. And so for right now, I think like if many chains did this at once, they can't handle the load of generating that many proofs. But that's like a pay more money and deploy more servers thing, not like a hard technical problem to solve.
Yeah, awesome.
So yeah, I'd say, and then also, I mean, Kona itself hasn't been audited yet, and there's some complicated logic in there. They've run it on multiple chains, like Genesis to tip, and had no problems, and it's tracked with what the implementation, like reference implementations, have done. So it's in good shape. But to deploy this as like securing a serious chain, I would want to see that audited, as well as the like the code itself that we wrote that's like verifying the ZK proofs.
Gotcha. We've got a question from the replies. How do you feel about how ZK, I'm changing my accent, ZK is developing today? We're slowly moving away from custom circuits and DSLs to ZK validation as compiler extensions for high-level languages.
Yeah, I have some thoughts. I'll preface with that I feel like totally unqualified to answer that. Like the surprising thing for me doing this was I was kind of gearing up for like, oh, okay, it's a ZK deep dive this summer, and it wasn't at all. It was like a how OP stack works and their assumptions and intricate Rust code and SP1 deep dive. But SP1 abstracts away the ZK stuff so much that like I definitely don't think I'm an expert at this at all. But one thing I'll say from working with SP1 that was interesting is like clearly there are benefits in efficiency in custom circuits versus something generic. Like that seemed obvious to me. That was like, oh, this is like really important and really like to be performant. Maybe this wouldn't be the right choice. And what I learned that's really interesting is there are efficiencies that they can get by because everything is verifying the exact same like basically like CPU logic of theirs, where for example, like they're able to really optimally like split up a proof and shard it across multiple like separate proofs and re-aggregate them without you even knowing. They've done some really cool work to implement GPUs, because all this stuff they are optimizing for proving one type of program, which is like the SP1 program, and then that can run any other program. And so I'm watching them have these like 5x, 10x improvements in speed over and over, as well as the ability to like leverage infrastructure that can move a lot faster than whatever like prover hardware you would otherwise deploy. And I'm starting to see that like it gets harder and harder and then never mind the security benefits of like I'm going to write Rust code and not custom circuits. So I think like I'm starting to see how like more and more like critical things that you would think would want custom work actually are probably better to be run this way. So yeah, I think like it's probably very likely. I mean, my experience with this was like I didn't think about building a lot of ZK stuff previously, and now I'm like, oh, there's like 10 ideas of like easy things I could build that are doing cool ZK things, because like they're like weekend projects now that there's not really much ZK involved. So I think it unlocks like a whole lot of extra use cases, and there's probably always going to be room for like the hyper to going into doing a bunch of assembly and Solidity code. Like there's always going to be a time where that matters, but more and more of what I'm seeing is like, yeah, the trade-offs of like speed and ease and security are probably more important in most cases.
Yeah, awesome. Cool. Let me just double check if there's any more questions in the replies. Don't think so. I think one more question from my side, like how did this project come to be? Like obviously I know you from the security side of things. How did this eventuate?
It was kind of good luck. I in the spring kind of decided like I want to spend the summer on more like on a project with a team that's probably not security focused. I was kind of missing the like building energy. And so I talked to a few teams, and out of the blue, the Succinct CEO just like cold emailed me for like as like a recruiting thing. I think they had like some automated thing they were doing to reach out to people. And I responded just saying like, hey, not looking for a job, but like if there's a magic thing that fits all these constraints, it might make sense. We chatted a little bit, and I've got a bunch of experience with OP stack stuff from security in the past. And she was like, oh, we're like talking optimism about doing this. Like it would be really helpful to have someone who's can like lead it and know our code and also know optimism stuff and just like kind of drive it forward. So just like was very fortunate that it lined up really well with like my weird constraints, my abilities, what they needed, timing, all that good stuff.
Yeah, that's awesome. Cool. Well, I don't think we have any more questions in the chat, but was there anything else you wanted to touch on before we wrap up?
No, that's it. I mean, yeah, I think if anyone wants to play around with it, it's kind of cool to poke around. And then more than that, honestly, I would say like if you have fun little like ZK project ideas to do with SP1, hit me up. I'm happy. Like they're like most early software, it's like changing so fast that it can be kind of like, wait, how do I use it? And like the docs haven't updated based on the code changes that went live yesterday kind of thing. So if you're playing with it, feel free to hit me up. I'm happy to kind of help walk you through it or hook you up with the team there to help. And yeah, if anyone's like serious about using this in production, I know Succinct is like heads down on getting it to that place. So I think we'll probably see that in the wild in the next 3 to 6 months or something. There'll probably be some audits popping up at some point for it too. So yeah, I think lots more interesting things happening on this. But if you're interested or doing anything in the area, hit me up. Always happy to chat about it.
Awesome. Thank you so much. This was great. And yeah, we'll be sharing the recording once that's ready to go as well. So for anyone watching this after, it'll be there.
Sweet. All right. Thanks, guys.